Okay, dear students, in today's lecture we are going to discuss about the stability of a system. Some systems they are stable by nature, while other systems they are naturally unstable. For example, just have a look at this system. If I want to levitate this nail against gravity using the magnetic force of this magnet, what I can do is that I can try to place it somewhere here at a spot where the gravitational force exactly balance the magnetic pull. Now, theoretically, there exists a point in between the magnet and the earth where the magnetic pull exactly equals the gravitational pull. If I can place somehow this nail at that point, then either I may be able to levitate it, but it doesn't happen physically. If I try to place it at that point, either it gets pulls up or no, or it drops down. So it's very difficult. It's not possible to place it at that location where the magnetic pull exactly equals the gravitational pull. But before we can try to develop a control system that can actually levitate this nail against gravitational pull, we need to look at the mathematics of this system and try to understand what is happening. Now, if we look at this system, then the force, net force acting on this nail is equal to the gravitational force minus the force that is actually being exerted by this magnet to pull the nail upward against gravity. So, this is the net force acting on this nail. So, this nail will be levitated when the gravitational force is exactly equal to the magnetic force. So, from here, from this equation, we can actually derive the transfer function of the system. Okay. Now, can you just bring to the transfer function? Okay, after all the mathematical calculation that I have explained in our class, we actually reach this transfer function. So, if I just look at this transfer function, this is going to have two poles, one pole at the right side of the S plane while other pole at the left hand side of the S plane. Can you just bring just this equation? I just want to see this equation. Okay. You see over here, one pole lies to the right of the system while other pole lies to the left of the system, and we have a negative sign over here. What this negative sign indicates that physically if I increase the current, then the distance between the nail and the magnet will be decreasing. So, this negative sign is actually showing this thing. So, the system can become stable only and only if somehow I can bring the right hand pole somehow towards the left of the system. For this we will have to design a compensator. Now, can you bring to the compensator design? Okay, actually this is the compensator and it has been designed by a resistor of 2 kilo ohms and 10 kilo ohms and a capacitor of 12 microfarad. So, can you bring to the circuit diagram? Actually, this is basically the compensator that has been actually designed. I have shown this compensator separately over here, and you have seen the transfer function in the last slide, and this is the overall circuit diagram that actually implements this magnetic levitation system. So, by using this system, what we are trying to do is that we are trying to bring the the right hand pole towards the left hand side of the S plane. So, if we can do it successfully, then what we can do is that we will get a magnetic levitation against the gravity, just like this. So, once it is levitated, if I give a small rotation to it, then it will keep on rotating. If I give it a small tilt or a vibration, it will keep on vibrating till infinity. Now, The most important thing about this thing is that this system has been designed using linear controller. Now, the limitation of this linear controller is that it is valid only in a very small region near to the equilibrium point. So, if I vibrate it and give it a vibration that moves it from away from the equilibrium point, then this system will no more be stable. So, for this thing I have to just place it just at the equilibrium point, and once it is placed over there, it will continue to stay over there. So, this is about today's demonstration. Thank you very much.